So now we're ready to begin. And should you choose to tune in at a later time, the reason I say that is, you guys like to put your hands on each other or what? Okay. So, should you choose, you can always tune into this at a later time, because I've always had the belief that when you're looking at someone else's work or even your own, you might not know why you did a certain step when you're trying to evaluate what you did. Okay? Maybe did it right, but maybe don't know why you had done a certain step. That happens more often when it comes to that of chemistry, upper level chemistry, more so than in here. Okay, so we have our problems. It says, as a student rides their bike, moving at 4.2 meters per second, turns the corner, and in 2.45 seconds is moving at 10.45 meters per second. What is the acceleration? I was thinking about doing something like this, but since we hadn't said it yet, I was going to maybe say this. Okay. Does anyone think they might know what that could possibly mean? What would a deceleration be? Just tell me.
Like slow down, like stop.
Yeah, and maybe approaching a stop, so it's slowing down. Deceleration or decelerating means it's slowing down. You can presume that if it's acceleration, it's probably positive. Not all the time, but the majority of the time. Okay, so you've read the problem. What is the next thing you should do? What's the next thing you should do? Can you be a little more, you're correct, but can you be a little more specific?
Write down the numbers or meters per second and time it took to turn the corner.
Right, because we just can't throw these numbers into a formula. They have to go in their specific spots. Okay, so what do we know in this formula, or in this problem?
Your bike is moving. He turned the corner at 4.2.
Okay, but first of all, maybe we should start here. What is your formula for acceleration?
Final velocity minus initial velocity.
Okay, so I'm sure we have all this wrote down, and we probably do. Okay, you always have that opportunity, but eventually, if you don't have this down, then you're trying to play catch up. Okay, so what do we know in this problem? Because it doesn't say this is the acceleration, this is the time, this is the speed. You have to look at what the label says. So if it's labeled in meters per second, what type of variable is that?
Is that an I?
Yes, that is an I. Yes, V and I. So if a number is labeled in meters per second, what variable is that? Or velocity. So when we say that, though, as we look at this formula, which one are we discussing, though? Okay, so this is where you use your English skills. Yes?
I cannot read that. It's just like a glare on me.
Well, you have the formula down, correct? Yeah, so you don't need this for sure. Okay? So this is where you can use your English skills to tell you which one's which, because it says the bike was moving at 4.20, it turns the corner, and then in 2.45 seconds, now is moving at 10.45. So does that tell you that 10.45 came first or 10.45 came second? It came second, okay? Because what that means, you're pedaling your bike, okay? You're moving at 4.2. then turn the corner, and then in 2.45 seconds, it's moving faster. Okay? So that tells you that 4.2 belongs here. So your initial velocity is 2. Let's put that for the time. 4.2 meters per second. What else do we know in the problem? What else do we know?
That we went 10.45 seconds.
Okay, meters per second. That's right. So what type of variable is that 10.45?
VF.
Okay, that is your final velocity. What else do we know in this problem?
That you went 2.45 seconds.
Okay,
Around the corner.
but then that's true, but what variable is that?
T. It would be your
That'd be your time. And we're labeling that in seconds. And then what is the question ultimately asking?
How fast you went. What is the
Okay.
acceleration?
Okay? So now when you get it to this point, again, you don't need to read the problem anymore because all your critical information is located there. So we just do what the formula tells you to do. Acceleration, there's our equal sign, and we've got a fraction. What goes up on top of your fraction?
4.20 and 10.45.
Okay? So we start with our final velocity, which is, as you said, 10.45 minus what?
420.
Okay? And of course we know that because it's written down over here in what we call our setup. And what goes on the bottom?
2.45.
So then the process that we have to do first is what?
10.45 minus.
You have to subtract first. And how do we know that other than that's what we told you to do? Because it's inside the parentheses. Okay. So take our fancy calculators. 10.45 minus 4.2 gives you 6.25, right? And divide that by 2.45. So we get 2.551. Does that second 5 change?
Yes. Yes. You round up.
No, it doesn't.
Yes, you do.
You-
It doesn't change.
It says 2.551, correct? So we're rounding to the nearest hundredth, which is 2 decimal places, right? So is that 1 big enough to change that to 2.56? No, it is not.
It's the same.
Stays the same. Okay? And how do we label that?
Meters per second.
Yeah. But if we just leave it like that, does that present a problem?
Yes.
Yes. So we have to label it as what?
Acceleration.
No. Your label here.
Time.
No. We said it, but I don't know if everyone knows how to apply it though.
Oh, deceleration.
So what gets squared?
The
No, in your label, something here needs to be squared. It's not this,
the meters per second. 5.
the seconds. That needs to be squared. Okay, that's how you do that. So, front row, right side, are we on the bus? Okay, middle. Okay? Left side, middle, 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 right. Okay? Back right, back middle, back left. Kind of in between there. Okay. All right. So the bottom one, I don't mean to be mean, but the bottom one is a lot more difficult than the top one. Did anyone work through and say, this one's a lot more difficult than the top one? Does anyone have an answer for the bottom one? Okay. What is it by chance?
I got negative 2.80.
Okay. You know, I think that's right. Okay. But there is just a slight problem with that.
Not negative.
Oops. But you just told me that you got negative 2. The problem with that. I would assume that you know how to label, which you probably do. I'm picking on you. I'm sorry. Okay. But what variable are you solving for in that bottom one? Velocity. What's problem with getting a negative value? Yes, velocity is positive. But the reason we haven't taught you that yet. Okay. So, in this bottom problem, a tiger is moving at 2.41 meters per second squared. So once we see this, what does that tell you that 2.41 is?
Times 2.
No.
Times each other.
No.
It's to the power of 2.
No.
It's the acceleration.
It's the acceleration. Okay? And changed directions. That's how accelerations will differentiate. Either there's a change in direction or there's a change in speed. That's how accelerations change. So that's why we say once this animal changed directions while moving at 10.10 meters per second, what can we presume that meters per second is? It's what type of variable? It could be. We're being too specific. It's a velocity. Because once we read a little further, okay, it says over a time frame of 3.03 seconds. Seconds is what type of variable? No.
Time.
It's a time. So then we can presume how fast was the animal moving before changing directions. So if its speed changed before it changed directions, that might mean you're solving for which velocity?
Initial.
You're solving for your initial velocity. That's why we're teaching you to look at what it says in the problem so you can pick the right variable. Okay, so we've read the problem. Next thing we want you to do, what do we know in this problem?
Acceleration is 2.41.
Okay, your acceleration is 2.41 meters per second squared. What else do we know?
That we have 3.03 seconds
Okay, and what variable is that?
time frame. Or
Oops, you're right. Well, when you say time frame, we just say time. Okay, so that's t. What else do we know?
we know that the animal moved 10.10 millisecond
Not millisecond, meters per second. Okay,
over and then won't
Okay.
that be VI? Or would that be VF?
VF. Okay, Okay, so I just want to walk around to see. We almost have this done. So that's your paper?
Yeah.
Where's your problem at?
Right here.
So you didn't write the problem down, you just wrote the numbers?
I solved it.
Okay. That's the first one. Where's the second one? You didn't, okay, so we're not wasting our time in here. Oh, okay. All right. Okay. Because we want everyone to have a good start at this, because just like we talked, this is get to be more difficult as we go, as it should. Okay, so we've got our setup down here. We don't need to keep reading in the problem. So what can we put on the left side of that equal sign?
A, or V, I,
No.
it'll be T under the fraction.
Okay, okay, let's look at our formula. What goes on the left side of that equation?
It'll be V.
What goes on the left side?
Velocities.
What goes on the left side?
Acceleration.
Say that again.
2.41.
Which is the acceleration. Right. Okay, tells you that right here. 2.41. Okay. So what goes on the top of that fraction? Okay, which is what value?
10, 10. 10.
Okay, and then what do we have left over?
The time.
Well, true, but I mean on top of the fraction.
VI.
Okay, and notice we have a question mark there for VI. And then what goes on the bottom of that?
Time.
Okay, and what is our time?
3.03
Okay,
seconds.
if we remember from yesterday, how do we get rid of our fraction? How did you, for instance, how did you do that in that problem you worked through earlier? You, what?
Typed in my calculator.
How can we get rid of our fraction? Did it in your first problem, and your calculator isn't always going to help you all the time. For instance, what did you do?
My calculator.
Oh, you're relying on your calculator too? All right. How can we get rid of that fraction? What did we do yesterday? Yeah, which means what? You're yeah, right. Okay. So where we see the squeaky wheel gets the grease. You ever heard that before? Yeah. So there's a lot of squeaking going on back there. So that's why we're spending more time back there. All right. So if we put this over 1, are we changing the value for that? No, we are not. It's still 2.41. I know, yay. Right? Okay. So, what do we do with these two numbers, 2.41 and 3.03? You're going to multiply those. Okay? So, upon doing that, 2.41 times 3.03, we get what? 7.30. Okay? And then, oops, I got that on the wrong side. Guess I just need to put that over there. Okay, So what is 1 times 10.10?
10.10.
Okay. And what do we have left over? Yeah, minus initial velocity. Now, there are 2 different ways that you can solve this, okay? Everything you did was 100% correct, okay? We just did not show you that final step. Yes?
What's the little symbol next to the V on the right side?
Yeah, it's a little I for initial. Okay, so that's probably about the 3rd time. How can we illustrate an I so that everyone knows what that is? How do...
You do a dot.
And you put a line. That is a kind of.
That is a dot right there.
Yeah, but it curves.
Oh, okay.
I do a little cap. It's like you did an L and then kind of.
Is that better?
Yeah.
Okay.
Well, that I that he had up beforehand was a shorter version of the cursive I, which you guys probably don't get.
I know.
All right. I guess one of the things I like to put a little curve on there so you don't think it's a 1. All right. So now we need to get VI by itself. So what do we do? No. Yes.
We take 10.10 and like minus it by itself, and then we do the same for 7.30.
That is correct. Okay. So let's apply what your classmate said correctly. I know what you said because I can remember you had said this. You said do that, but when we do this on the left side, or excuse me, the right side, what do we need to do to the right side? I'm getting my sides. You did it to the right side, we got to do it to the left. So then 7.30 minus what you said, 10.10.
And it equals 2.5.
I don't know if it's, I think isn't it 2.87 or something?
Negative 2.8.
Okay, so 2.8. See, that's the problem that we have right now. Equals. Okay. So this is where we got to our final step. Yes.
Once you take negative 2.8, and once you make the VI a 1.
You're close. Okay. But as we said earlier, probably 10 minutes ago, what's the problem with this final answer right now?
It can't be negative.
Yeah, you can't have a negative velocity. So there's one of 2 things you can do. Okay? What happens if you take a negative number times negative 1? Get a positive number. You can divide this whole thing by negative 1, or you just would say, I'm multiplying everything by negative 1. When that happens, that makes that positive. So initial velocity has to be 2.8. Oh, and the label, which is what? Meters per second. Okay? Make sense? Front row, are we on the bus here? You correctly told me what to do. I think you're at least at the bus stop. How's that? Okay, well, we'll continue to work at that. We're on the bus. Second row. Third row. Now, a lot of you are being honest with this and saying, no, I'm not, or maybe. And some of you are saying this, and maybe you are, but you're not doing yourself any favors if we're having problems with this and not addressing those. Okay, so one of the things we do to supplement this is, why not watch about speed? Okay? And that would be as follows. Okay. Has anyone ever heard of this show?
Yes.
We make reference to this quite a bit.
Yes.
Okay?
It seems the faster we can go, the better. From turbocharged racing vehicles to supersonic military craft, Modern Marvels has covered a vast array of speed-boosting advances in the world of high velocity. Now we've selected 10 that we're taking on a supercharged charging out of the gate at number 10. Tank with achieve high speeds. The EF is 3 times in water. It can go nearly 28 miles per hour. And on land, 45 miles per hour. Like a kid's transformer, our number 10 vehicle easily converts from a land tank to a high-speed armored watercraft. On water, the expeditionary vehicle can hit speeds never before seen in an amphibious tank. The source of that speed starts with its twin water jets.
Comes out here, and what it is what we got basically is a giant jet ski.
A lamp called a ground lamp opens up on the front end and reduces the vehicle's water resistance. That allows its bow to rise higher above the surface, and for the armored craft to pick up speed. The tank's underside can also be quickly reconfigured for maximum speed.
Underneath here we have these giant metal flats, and they are called the chine flaps, and they open up and they will close and create a complete flat bottom boat. And it's just like adjusting the trim on a boat. It gives us our trim and angle to help get the vehicle up onto plane.
You can't move fast without a powerful engine. In this case, a specially engineered MTU diesel engine.
It's a 12-cylinder, 90-degree V design, creates 2,700 horsepower in water mode and 850 horsepower in land mode.
Drivers can channel the engine's horsepower effectively using controls that serve double duty on land and sea. The high-speed EFV has come a long way since the first amphibious tanks, called alligators, rolled out of the sea and onto the beaches of the Pacific in World War II. The alligators proved their worth by successfully ferrying men and supplies over treacherous coral reefs and onto the beaches. But they could go less than 9 miles an hour in the water, and not much faster on land. Today's amphibious tanks are a big improvement. There's no doubt the Marine Expeditionary Fighting Vehicle has speed on its side, even with heavy armor plating. A composite mesh material that can withstand 14.5 millimeter armor-piercing rounds, fired from 300 meters. That tough skin comes in handy as the vehicle morphs from sea to land. Along with faster speed, this amphibious craft has more firepower, Another reason it comes in at number 10 on our countdown.
The vehicle's fully stabilized, has second generation forward-looking infrared, 30mm cannon, and a 7.62 coax. And that Marine no longer has to gauge the wind. He can just essentially put his crosshairs on a target and destroy it.
From this fast-moving amphibious beast coming in at number 10, we're staying on water for number 9, but pushing the speedometer. It's a high-speed catamaran ferry. Meet the Cat, one of the world's fastest ferries.
CAT is a high-speed, twin-hull, catamaran-style ferry, one of the largest of this kind of ship in the world.
Everything about this remarkable vessel was made for speed. Its unique twin hull raises it above the water. That means less water resistance and more speed.
You never really get used to the power that's involved here. You can get up to 40 knots in probably 2 minutes. It's still quite a feeling.
This high-speed ferry currently runs routes between China and Taiwan, carrying up to 220 cars and 900 passengers at speeds close to 40 knots, twice as fast as traditional ferries. The secret to its speed is a specially designed aluminum hull that's strong yet light on the water. When the boat's two slim hulls encounter a wave, they cut through it rather than over it. This stabilizes the craft for a safe and fast ride. Combine that design with 38,000 horsepower from 4 turbocharged engines, and you get the Cat's jaw-dropping speed that's earned it the number 9 spot on our countdown. From the bridge, the crew controls the engines and their corresponding jets.
Basically, it's the exact same principle as a jet ski, but just on a much larger scale with much more power. The water is taken in through an inlet and put through an impeller, and that water goes through a stator bowl, which takes the twist out of the water and shoots it back out through the nozzle. And that's what provides all the thrust that gives the ship its power.
At top speed, the 4 jets shoot water through at over 4,700 gallons per second. At that rate, they could fill an average backyard swimming pool in under 5 seconds. Incat, the ship's builder, has been making fast catamaran ships like the two-hulled Cat in Australia since 1984. And if you thought a two-hulled boat could move, check out the speed of this 3-hulled trimaran called the Earth Race that beat a world speed record in 2008. This super-light carbon Kevlar composite vessel circled the globe in just 60 days, 14 days faster than the previous record. The Earth Race's 3 hulls can slice through waves up to 50 feet high, and the entire vessel can totally submerge at a depth of 23 feet for a few seconds. Be on the lookout for more multi-hulled vessels speeding across waterways around the world. From high-speed amphibious tanks to high-speed ferries, we've started our countdown racing on water, but we're rolling back onto land and putting the pedal to the metal for number 8. Things are going to get even speedier as we race to number 1, a craft so fast it could rocket from Los Angeles to New York in just over 20 minutes. We're flooring it, celebrating the thrilling world of high velocity. We're showcasing 10 of our fastest marvels and counting them down to the speediest one of all at number 1. We started off with some speed demons on water. At number 10 was the swift-moving Marine Expeditionary Fighting Vehicle. Coming in at number 9 was the world's fastest catamarans. For number 8, we're racing onto land. They're big, they're bold, and they're fast. They're Bigfoot monster trucks. If there's proof that supersize doesn't have to slow you down, it's this beast. In the fast-paced world of high-flying monster trucks, where 10,000-pound vehicles rule the track with 1,500 horsepower, one icon stands above all others, Bigfoot, which has dominated the sport of monster trucks. In fact, it set the record for both speed and length of jump, when it vaulted a 727 airliner in 1999 at 69 miles per hour and 202 feet. Speedy enough to come in at number 8 on our countdown. Bigfoot's world-famous speed and strength is all thanks to one man's oversized vision. That's Bob Chandler, who first started tricking trucks out with giant tires back in 1975. Big tires called for a stronger axle. A stronger axle called for a bigger engine. The added weight called for a stronger frame and suspension.
So it was a vicious cycle till it got to the point where I run these 66-inch tall tires. My general manager, Ron Magruder, started calling me Bigfoot because I couldn't keep my foot out of the throttle. And I liked the name, so I stuck it on the side of the truck.
Today, Bob Chandler's Bigfoot is the one to beat at monster truck competitions. Here, skilled drivers race their giants over jumps at speeds up to 70 miles per hour. To withstand that kind of abuse at big speeds requires big strength.
To make it strong, the frame has to be strong, the axles have to be strong, the engine, the transmission, the whole vehicle has to be strong.
Bob builds his shock-absorbing speed powerhouses in a 24,000 square foot garage in Hazelwood, Missouri.
This is one of the current chassis we use right now. Chassis kind of in construction. You can see this. This is the main frame right here. We run a nitrogen gas shock, which is so much stronger than our leaf springs. It absorbs so much more energy. It cushions the ride for the drivers.
These shocks allow 25 to 30 inches of suspension travel to help absorb the impact of launching 10,000 pounds of truck at 70 miles an hour, 20 feet in the air. You can't go high speeds without strong wheel axles, and Bigfoots are top-of-the-line German-made.
ZF axles is what they're called. And what makes them so strong is the planetary is right here at the wheel hub. So it transfers, all the power going to it is reduced right here.
In a planetary gear, all of the gears are grouped around each other on a single plane, like the planet.
Okay, we're not done with this. We'll continue with this video. One of the things I wanted to mention is one of those monster trucks you saw jump over the top. What happened to one of their front axles? It snapped right off of there. That's a lot of the things that we do with problem solving in here. Sometimes some of you are going to get a problem where a structure fails. Some of you will get a problem where the structure works. It's not a failure because that's just one of the things that we solve for. Looking at next week, chances are we will have your vocabulary due on probably the 29th, which is a week from yesterday. We'll have, that's an assignment, but we haven't formally assigned it. We'll do that on Monday. We'll have your first worksheet that we will assign probably on Monday. So when you walk in, look over at the board, and we'll have the week mapped out. I like to tell you what it is that we're doing, and then I write it down later. Yes, what? Nope, you keep those problems. That is for your reference and to look at. Okay, so we will catch up to you next time.
Can we congregate?